For chapter 11, it asked to show that you can write the kinetic energy of an object rotating about a fixed axis with angular momentum. Asked if it could be written as k equals L squared over 2I. Now I just took the rotational kinetic energy equation of k equals 1/2 times I times omega squared. And then I multiplied that right side by I over I to get 1 times I squared times omega squared over 2 times I. And then since L equals I times omega, I just substituted that in. And then that gave me k equals L squared over 2I, which proves that it can be shown in this manner. Now for chapter 12, I chose question 10, which asks to find the mass of the different objects that were hanging off this three-tiered mobile. Now since I knew this object was a rigid object in static equilibrium, I knew that the sum of the net torques had to be equaling 0, so that's why in the following equations everything is equaling 0. Additionally, since because of the way the mobile is structured, I had to begin calculating from the lowest most rod going up to the top, because some of these rods are connected to one another, meaning that some masses are going to be needed to be calculated before others. So starting at the lowermost rod, object M4's mass was already given as 12 grams. So into the equation, I plugged in 12 grams times g times 3 centimeters minus m1 times g times 4 centimeters equals 0. And then solving for m1, the mass is found to be 9 grams. The equation is modeled this way because torque equals the vector position times the force. And then I subtracted the two torque equations because they're going in opposite directions, and they also have to equal 0. Going up to the middle rod, we're going to be using the same format of equation of torque, and then it is going to equal 0 because we're in static equilibrium. So we're going to be doing m2 times g times 2 centimeters minus 5 centimeters times 21 grams times g. And the 21 grams comes from the total mass of objects m4 and m1, since it's being attached to the middle rod. Now in the case for the top rod, we're going to be emulating the same format of equation, and so the equation is going to look like 4 centimeters times g times 52.5 plus 21. 52.5 is the mass of M2 that we just calculated, and 21 is the mass of the last rod that is all attached to the top one. And then we do minus 6 centimeters times g times m3 equals 0, and then the mass of m3 is calculated to be 49 grams. Alright, so for chapter 13, question 1, it asks to calculate the gravitational force between two spheres, treating each as a particle located at the sphere's center. So to solve this problem, we're going to be using Newton's law of universal gravitation. The equation is F equals g, which is the universal gravitational constant, times m1 times m2 over radius squared. So g equals 6.674 times 10 to the negative 11th newtons times meter squared over kilogram squared. So I implemented that into the equation and then put in the masses of the two different spheres and then plugged in the radius, that is the distance separated between the two masses, and I got F to equal 7.41 times 10 to the negative 10th newtons. So for chapter 14, I chose question 1, and it asks for the pressure exerted by the chair onto the floor per each leg of the chair when a large man is sitting on it. So I use the pressure equation of pressure equals force over area, so that is pressure equals mg over pi r squared. given in the problem is the mass of the large man sitting on the chair, and that totals to 95 kilograms, and the radius of each circular leg of the chair is 0.5 centimeters. So plugging that all in, I plugged in 95 kilograms and 9.8 meters per second squared in the numerator, but then I divided that by 4 because there are 4 legs of the chair, and the force is going to be evenly dispersed throughout each leg. In the denominator, I converted the radius from centimeters to meters, plugged that all in, and then calculated the pressure for each leg of the chair to be 2.96 times 10 to the 6 pascals.